So our next speaker is going to be Shohana Iffat from the University of South Carolina, Columbia.
So, good afternoon, everyone. My name is Shohana Iffat. I am from University of South Carolina, where I am acting as working as a PhD candidate and going to present amendment of cement paste with low concentrations of well-dispersed, partially unzipped carbon nanotubes, which was a collaborative research between University of South Carolina and Savannah River National Lab. Here, our colleagues are Fabio Mata, Jay Gaylord, Mark Levington, Mithun Siddar, Mohamed Balusa, and Spencer Tinky. So the objective was to explore low concentrations of oxidized partially unzipped carbon nanotubes, which is named as PUCNT, as amendment for cement paste. So PUCNT here acting as a novel material for application of cement composites. Also, we considered low concentration in range 0.001 to 0.05%, where 0.05% was reported as lower bound concentration of multiwalled carbon nanotube application in cement composites. Also, we considered lowering this concentration by 1 order of magnitude. So, we used oxidized partially unzipped carbon nanotubes here, as carbon nanoparticles are hydrophobic in nature and it's difficult to disperse them in water directly. Also, functionalized nanoparticles can create bonding with calcium silicate hydrates in cement matrix. So, these functionalized nanoparticles can act as nucleation sites for cement hydrates. Also, they can fill up the pore spaces between CSH gel, which helps to densify the cement composite matrix. Also, these nanoparticles can bridge the nano and micro cracks and prevent the propagation of these cracks to form larger cracks. In this way, with application of carbon nanoparticles, enhanced mechanical properties could be achieved in cement composites. Now, why we are considering low concentrations? Now, if we consider high concentrations like 0.05%, there will be some agglomerates of carbon nanotubes inside cement matrix. That's why the total actual surface area covered by these nanoparticles could not be efficiently utilized. And if we can lower the concentration, they will evenly distribute inside cement composite matrix, and we can take the advantage of utilizing the total surface area covered by those nanoparticles. So there will be no wastage of particles, which will eventually reduce the construction cost for large concrete structures. In a previous part of this research funded by US Department of Energy, we applied 0.001 to 0.05% of multiwalled carbon nanotubes in cement paste and obtained in range 20 to 25% more compressive strength compared to the control sample. So, increasing in concentrations by 50 times from 0.001 to 0.05% did not significantly enhance the compressive strength. We also obtained the total porosity from mercury intrusion porosimetry and found on average 17% reduction in total porosity from this concentration range of multiwalled carbon nanotubes. Also, we noticed that the pore size mainly affected less than 50 nanometer diameter. So, if we increase the concentration from 0.001 to 0.05, but like 50 times increasing in concentration had limited effect on total porosity. On the next step, we estimated the specific surface area from the molecular structure of multiwalled carbon nanotube and graphene nanoplatelets, and then using the bulk density of cement paste and the concentration range, we estimated the surface area covered by multiwalled carbon nanotube or graphene nanoplatelets in 1 cubic meter of cement paste. It is observed that for multiwalled carbon nanotube, approximately 10 to the power 3 to 10 to the power 5, the red lines here, And for graphene nanoplatelets, approximately 10 to the power 4 to 10 to the power 6 meters square of area can be covered in 1 cubic meter of cement paste. So these low concentrations are actually not low concentration. These are huge concentration which produce large amount of surface area. Now, if we can unzip the outer layers of multiwalled carbon nanotube, we can even increase the surface area for the similar concentration range. That's why we tried to change the morphology of multiwalled carbon nanotubes, which are concentric cylinder having several shells inside, and only the outermost surface can take parts in chemical bonding. So if we can unzip the outermost layer longitudinally, we could enhance the open surface area. Also, more functional groups could be attached through the large surface edges. At the same time, a hybrid structure will be generated with comparable aspect ratio to the original multiwalled carbon nanotube, which will help to facilitate mechanical amendment in cement matrix. So the pristine carbon nanotubes were soaked in O-phosphoric acid and sulfuric acid with an oxidant potassium permanganate. Then the stock solution of PUCNT was diluted was sonicated to prevent re-agglomeration. On the next step, the functionalization was verified through FTIR spectroscopy, and CO bonds were identified, which indicates active carbon sites. Also, we performed Raman spectroscopy and found active carbon sites by finding the width and intensity of D band, which is more in case of PUCNT compared to the multiwalled carbon nanotubes. Next step, the PUCNT stock solution was diluted with additional DI water to get the required concentration. As the initial pH of the solutions were found near acidic pH range as they were acid treated, to increase the pH to protonate the functional groups, we added negligible amount of sodium hydroxide to the suspensions and checked and verified the effect of sodium hydroxide itself on the mechanical properties of cement composites by performing uniaxial compression test. And we found no significant enhancement in strength due to addition of sodium hydroxide itself. On the next step, we observed the suspensions visually, and we can see that for 0.001% almost transparent solution was obtained, and with increasing in concentration, the solution is becoming darker, which indicates tendency of agglomeration. So the stability was verified through dynamic light scattering in terms of average hydrodynamic size and zeta potential, which we monitored for 10 days. It is found that for 0.001 and 0.001 and 0.005%, almost similar range of average hydrodynamic size is obtained, and for 0.05%, comparatively higher average hydrodynamic size is obtained. So if we increase the concentration, there will be limited gap between the particles inside solution to diffuse freely, which affects the stability, which we observe from zeta potential measurement, from where we can see for 0.001 and 0.005%, more negative than 30 millivolt of zeta potential can be obtained, while 0.005% gave only around -5 millivolt of zeta potential, which indicates unstable aqueous suspension. On the next step, we prepared cement paste prisms with 1 inch, 1 inch, and 3 inch dimensions, and with the PUCNT suspensions and ordinary Portland cement using water to cement ratio 0.5, and cured the prisms under saturated lime water for up to 28 days. And we can see that after 28 days of curing, we got 10%, 29%, and 14% more compressive strength from 0.001, 0.005, and 0.05% concentration. So 0.005, which is this green bar, gave more compressive strength compared to the 0.05% of concentration. We also obtained the elastic stiffness of the paste by obtaining the slope of load deflection curve in elastic range, and similarly 0.005% gave more elastic stiffness value compared to 0.05% after 28 days of curing. So to verify the reason behind this kind of enhancement, we took the failed sample after compression test and observed under SEM microscopes. So this is the distribution of PUCNTs indicating by the blue arrows and circles after 14 days of curing. For the 0.001 and 0.005%, we can see no visible agglomeration and almost uniform dispersion inside composite matrix. But for 0.05%, we can see several circles indicating PUCNT agglomerates. So these agglomerates might reduce the homogeneity of the matrix by forming some defect sites, and that's why less significant enhancement in strength and stiffness was obtained. So this is the nanomicrostructure of after 28 days of curing, where similarly we can see for 0.005% uniform dispersion, and for 0.05% some CNT agglomerates were located. But this concentration, like 0.05%, gave some enhancement compared to the control sample. That's why we observed the microscope in more detail. And after 7 days of curing, we can see several needle-like ettringite was located for the control samples having larger size pores, while with PUCNT added samples, we can locate several amorphous or fibrous calcium silicate hydrates near the location of PUCNTs. Also, we can identify several smaller size pores. So, pore refinement and calcium silicate hydrates formation with addition of CNT indicates that PUCNT might act as nucleation sites for hydrates. So this is nanomicrostructure after 14 days of curing. Similarly, for the control sample, we can see several ettringites, and for PUCNT added samples, we can see several calcium silicate hydrates here, indicating by the yellow circles near the location of PUCNTs, which indicates preferential hydrations. Also, several smaller size pores are identified. So pore refinement and preferential hydration was obtained with addition of PUCNTs. Similarly, after 28 days of curing, we can see several CSH and small pores for PUCNT added samples. And for control sample, instead of ettringites, we can look at some plate-like calcium monosulfate hydrates, which are also transformation of ettringites and calcium aluminates hydration products, while calcium silicate hydrates are the hydration product of tricalcium silicates. So, pore refinement and preferential hydration resulted in less porous structure with PUCNT addition. Also, we observed the pre-curing surfaces which were in direct contact with curing water, and we can see for the with duration of curing there is a modification of surface structure which is the resultant of hydration. Also, we can see the similar result with addition of PUCNTs. Smoother surface is obtained, which indicates accelerated hydration, which we already observed from the nanomicrostructure observation that CSH was formed whenever we added PUCNTs inside cement paste. This is the larger magnification image. So this is for control sample after 14 days of curing, and this is for 0.005% of PUCNT added sample after 14 days of curing. Smoother surface is obtained here. So this is another example after 28 days of curing. So where we can see smoother surface with PUCNT addition. So as I don't have enough time, I am trying to make it short. So in conclusion, we can see that for PUCNTs oxidized and dispersed in aqueous solution, stable aqueous suspension was obtained from 0.001 to 0.005%, but unstable aqueous suspension was obtained for this concentration, which is 0.05%. Improved formation of hydrates and surface structure was observed for all concentrations of PUCNTs, while agglomerates inside cement paste was identified for only 0.05% concentration. That's why more significant enhancement in compressive strength and elastic stiffness was obtained from 0.005%, and less significant enhancements were from 0.05%, as we could not achieve the uniform dispersion of this concentration, not in water or not inside cement composite matrix. So instead of increasing the concentration of carbon nanotubes, if we can look at lowering the concentration, we don't have to apply additional dispersion technique. We can just simply utilize the total surface area covered by these low concentrations of nanoparticles. Also, we can, if we can unzip the outermost layer of multiwalled carbon nanotube, this will increase the surface area. So we can take that advantage by reducing the concentration so that we can uniformly distribute the nanoparticles in cement composites, which will enhance the mechanical properties with reducing the total cost. So that was all. I would like to thank US Department of Energy, Savannah River National Lab, and Department of Civil Engineering, Arnold School of Public Health, and Electron Microscope Center of University of South Carolina. Thank you all. I would be happy to answer any question if you have. Thank you.
Thank you, Shohana. Very nice talk. So there are two questions in the chat that I see, and I think they're related. So what is the advantage of using the PUCNT compared to graphene? Because I guess with CNTs, they're rolled up graphene sheets. How is partial unzipping different from that of graphene?
Okay, that is a very good question. So why not graphene and why not multiwalled carbon nanotube? Actually, this is a hybrid structure in between multiwalled carbon nanotube and graphene nanoplatelets. So if you see that, if I can unzip the outermost layer, the comparable aspect ratio of multiwalled carbon nanotube can be achieved, which we cannot consider for graphene nanoplatelets because this is if we fully unzip them, we will reduce some aspect ratio. Aspect ratio is also essential for the mechanical amendments like bridging the cracks and other properties inside cement matrix. So partially unzipping will at the same time increase the open surface area and functionality, so they can help to precipitate more hydrates. At the same time, the mechanical amendment can be achieved through achieving the comparable aspect ratio.
Thank you very much, Shohana.
Thank you.